Okay, so second half of lecture 5, we just covered the intermediate value theorem. That theorem had to do with continuous functions over closed intervals. Next up, we need to discuss infinite limits. And by that I mean, sometimes as x is approaching some value c, a function will start to blow up. By that I mean, as you get closer and closer to c, the function, if you evaluate it, it starts getting bigger and bigger and bigger. It's not heading towards a number, it's just getting arbitrarily large. Or it's getting more and more negative, negative, and negative. It's becoming arbitrarily small or arbitrarily negative. It's just it's blowing up, it's going away. Like literally the function's values are just going to shoot off. In fact, let's start with an example, just to like illustrate the point before we define anything formally. So consider the function f of x equals to, I don't know, 1 over x minus 2. Okay, so this function is not defined when x is equal to 2, right? And if you know like your parent functions, like if you know what 1 over x looks like, it's like that. It's just that thing shifted over by 2. So what does it look like? I'm the best to draw this flow. So 1, 2. It's like my new y-axis in a sense. It should look like this. On that side of 2, and then on this side, it should look like that. Okay. Now, notice what happens, like if this is like our C. Right there. What's happening as we approach 2 from x larger than 2? Right, like we evaluate like here, there's the function value. We evaluate there, there's the function value. Evaluate there, there's the function value. As we get closer and closer, it's blowing up. It's just going off to infinity from that way, right? And it's because we're dividing by smaller and smaller numbers. Remember, when you divide by like a fraction, it's the same thing as multiplying by the reciprocal of that fraction, right? So like, just to like recall some algebra, 1 divided by a over b is equal to b over a, right? Same thing. So when we're getting closer and closer to 2, so we can't plug in 2, right? But when we're really close to 2, this is a small ratio. It could be like 1 over a billion, right? So 1 divided by 1 over a billion is a billion. Which means we're going to be way up there on the y-axis. It's blowing up. So what about if we approach x equals to 2 from the left-hand side, from x that are smaller? Well, the same thing is happening, except for now, we're dividing this ratio by negative ratios. So it'll be like when we're really close to 2 from the left-hand side, it's like 1 over negative 1 over a billion. So it'd be negative a billion. So then we're shooting down that way. Okay. And this is actually why you can't divide by 0, right? You can't divide by 0 because as you approach that process of actually putting in a 0 there, you're dividing by a really large number. In the function, 1 over x, you treat it like a function, it's going to blow up. Same type of thing here. Okay. So our goal with the rest of this lecture is to kind of understand the different ways which this can happen, and then also learn how to define these things. This is called a vertical asymptote for the graph of the function. Okay. So maybe I can write down the formal definitions over here, and then use that side of the board to like do examples. Definition. Okay. So let f be a function that is defined at every real number on some open interval containing a number c, and it's defined on every number in that interval except possibly c. Okay. Then here's the definition part. All right, so we write the limit as x approaches c of f of x is equal to infinity. We write that, but let me elaborate on that in a moment. If and only if, and if you recall from a previous lecture, if and only if is like the logical version of equivalence. So whatever I write here, it proceeds the statement, whatever I write after it is an equivalence to that. Okay. Okay, so we write that that's infinity if for each positive number m, there exists a delta greater than 0, running out of room, this ST right there, such that, okay, I had more room, I'd write it out, but such that x minus c less than delta implies f of x is greater than m. All right, so it's going to take me a moment to describe what's going on with all this fancy notation and stuff like that. Okay, first off, this is a little bit of abusive notation right here. Infinity is not a number. It's a process. Right? It's a continuous process of just adding and adding and adding and adding and adding and adding, getting larger and larger and larger. So that's not a number. So technically, this equal sign doesn't mean it's equal to a number. It's equal to this just means it's unbounded. The function's getting arbitrarily large, which actually might hint at what's going on with this equivalence right here. Right? So I'll say it out loud again. The function f is unbounded as x approaches c. Unbounded. Nothing can stop its growth. Right? So if and only if, what is this next part, which should be equivalent to that idea of being unbounded as x approaches c? For each positive number m, each positive number, so m is a positive number, right? There exists a delta greater than 0. That's probably annoying to all of you. But look right there. What did I really try to emphasize about the absolute value of the difference between two numbers? What does that mean? Distance, exactly. So let's say it with using our words and not these ugly symbols. For each positive number, there exists an interval around c of distance, of width, or radius, I mean delta. So there's a positive number such that if x is within distance delta to c, then f evaluated at x is greater than that positive number. Think about that, right? Like, for example, like consider the function equals to something like let's do this. That. Okay. So this is that same function that we were looking at, basically, just it's squared, it's like it's growing faster. But now it's also positive always. So what does this look like? It looks like this. Right? To make life easier, let's just focus in on this function on the interval negative infinity to 0. Let's just focus in on that interval so we can exclude this business right here. There it is. There's the function f right there. Okay. So again, this piece right here, we said it out loud, means that f is unbounded as x approaches c. Nothing can stop its growth. This other piece, which is equivalent logically, because I wrote this if and only if right here, means that for any positive number you pick, there's some interval around c, so that if you pick an x in there, f is greater than that positive number. So like, that's a positive number right there, right? So what this is saying is that there's like an interval around 0, right? So that if we're close and if we're in here, we're above that value. That's what it's saying, right? Like this is like distance to 0 is within delta. It's like 0 plus delta, 0 minus delta. Right? This is saying there exists some interval, some delta that makes that interval, so that whenever x is in there, we evaluate the function, it's past that m. And this is for any m that we choose, right? Which we know that this thing blows up, right? It just goes off to infinity. Which means that how could we ever like not, like, no matter what m that we picked that was positive, we could always find an x that gets shot above it for any x in that small interval around c. Okay. So this is what it means for the function to go to infinity. Okay. Now, that's an example of it. As I mentioned in a previous lecture, you should have an example of the thing in question, the definition, but then also a counterexample. That's something that doesn't satisfy the definition. So there's an example, what about a counterexample? Well, a slight modification. So our function would be maybe like f of x equals to 1 over x. Now again, plot this guy out. Looks like this. We want to look at the limit as x approaches 0 of this thing. Like, is that unbounded according to this definition? It depends. It depends on the side that you're looking at it, right? Because if we're going to 0 from this side, it's dropping down to negative infinity. If we're coming at 0 from that side, we're going to positive infinity, right? So does that satisfy this definition? Well, let's just like assume that there is some like, so pick some positive number, maybe like m right there, right? And then, so on the right-hand side, yeah, this is like 0 plus delta, 0 minus delta, right? There's a detail in this such that we have to be very careful of here. This must imply that for any x in that interval, any x within distance delta to c, right? Now, yes, if we pick x over here, it's like above m, right? Like any x we pick over here, it'll shoot up over there. However, those x on this side of 0 are also within distance delta to 0. If we pick any of these x, oh, it's down here. It's less than m. So this condition right here, this conditional statement, if that, then this, does not hold for that example. It holds on the right-hand side, but does not hold on the left-hand side. In fact, we can just write that out because we know about one-sided limits. The limit as x approaches 0 from the right of 1 over x, we can say that equals infinity. But on the left-hand side, this equals minus infinity. So because these don't match up at infinity or negative infinity, they don't match, not going to the same place. This right here does not exist. It's because the left and right-hand side limits don't match up. They don't go to the same place. So just something to be careful of, right? And that was almost kind of implied with the previous example, because I noticed I truncated the domain, but if I would have left it the same, it would have satisfied the definition still, because on the left and right-hand side, they're both going up. And I just wanted to focus in on one side to make it easier to think about it first. But hopefully you see the original example I had, 1 over x squared for x in the interval negative infinity to 0. Hopefully that was, if you extend that to negative infinity to infinity, it still satisfies that definition. Okay, so, oh, we didn't define this, negative infinity. How do you think that we could modify this definition to kind of handle the negative infinity case. So it's like this left-hand side here. It gets arbitrarily negative, right? So it's unbounded in the negative sense. So maybe for each m less than 0, there exists an interval around C so that f of x is less than m. That would be how to modify this for the negative case. All right. Which hopefully this makes sense. But whenever these occur, whenever we're heading towards infinity, in all of these cases, it's almost like we're defining an asymptote at x equals to c, whatever the c may be. And that's the next definition. Okay, so definition. So if f of x approaches infinity or negative infinity as x approaches c, then the line x equals c is a vertical asymptote of the graph of f. All right, so all of you have probably seen asymptotes in college algebra or pre-calc, but if you think back to it, you don't know the limiting process. It's difficult to determine when there's a removable hole in the graph or a vertical asymptote if you don't know about the limiting process, right? So this is where things should start to get easier. Now, I know calculus has like a reputation of being like a difficult class, but honestly, it's easier than pre-cal and college algebra if you have the right instructor and things are conceptualized the right way. The tools of calculus make solving problems a lot easier. Again, how would you even define a vertical asymptote in college algebra or pre-cal? It's like there's like checks for division and then division by 0 or some problem like that. Like, now we have the tools, right? We look at where the function's going as we approach the problem area from the left and right. If they match up at a number, that's not a vertical asymptote. If the function blows up, that's a vertical asymptote. Okay. So let's look at some examples. So, oh God, I have to write a theorem down first. And it's really long. I don't even want to write it out. I guess I have to. Before we're doing that, we have a theorem. And for the sake of brevity, I'm going to try my best to piece up the statement of it into like bullet points to not take up too much time. Okay. So F and G are continuous on an open interval containing C. Okay. F at C is not equal to 0, and G evaluated at C is 0. Okay. What else? There is an open interval around C. Such that, so I guess I'm just going to start doing that every time. ST is such that G of X is not equal to 0 for all X in this interval. Okay. Okay, then we're ready. If these things hold, then H of X equals to F of X divided by G of X is a vertical asymptote of F. Well, I should be very specific with that. A vertical asymptote of F at X equals to C. Yeah. I'll read this at X equals to C. Okay. Now, I definitely needed to write this theorem out and kind of talk our way through it with an example, because this is the main theorem to find the vertical asymptotes of a given function. So it's like a very applied type of theorem for homework problems and things like that. Okay. So, let's see. Example. So H of X equals to 1 over 2 times X plus 1. Okay, so we might be asked to find the vertical asymptotes of that function. We should have a vague idea of how it looks. Right? It's like that. Okay. But we can apply this theorem to it to find the vertical asymptote. So I ran out of room, but I would have typically wrote find the vertical asymptotes of this function. It's a problem you would encounter. All right, so solution. So I'd say let f of x equal to the constant function 1 and g of x equal to the function 2 times x plus 1. I'm setting it up to match exactly the statement of the theorem right now. And for those of you that are interested in mathematics, and then also for those of you that might have struggled with mathematics in the past, letting things like that, like just let this be this thing, and then working with that is sometimes easier than trying to mentally arrange things, right? I have a pretty bad memory, so if I was trying to apply that theorem to this, I'd have to like somehow remember, okay, F, G, and then look back at the theorem, it's long, it's gonna, oh, what's F again? Like these are problems that you might encounter, right? So just saying, let that be that, it's on the paper in front of me, I can just look at it. Okay. All right, so those are continuous functions. So when looking at statement of theorem, they are continuous. And what's the value of C that I might want to consider? Well, it's the problem area, right? So C equals to -1 might be the problem area. So possibly, I should say, well, maybe I'll just say let it. That's the place where that function h would have some issues. You'd have division by 0, okay? And we're going to wonder or question if there's happens to be a vertical asymptote at C equals to -1, or if that's just some removable discontinuity. Right? Okay, so f of 1, well, that's just 1, that's fine. G of 1 is equal to 0. So I'm slowly taking off the hypothesis of this theorem. Okay, is there some interval around -1 where G is not equal to 0? Yes, right? This function right here doesn't exist at -1, but everywhere around there does exist. So it does satisfy the next part of the hypothesis. Okay. Now we're at the implication. What does it imply? And is that implication useful for us? So, oh, we're done. we're done. Maybe I'll write it out to be very explicit. So note g of x is continuous around c equals -1, or note g of x is not equal to 0 around -1. That's the same thing as like the bullet point there, which implies that by this theorem, h of x equals to f of x over g of x. Well, what are those things? I can look back up here and see what it is. It's our original function. Is a vertical asymptote at x equals to c. Did I say that wrong? Has, I knew it. It should be has a vertical asymptote. So this thing here, by that theorem, has a vertical asymptote at x equals to -1. Done. That's the solution. All we did was check off the conditions of this theorem, and then the implication of that theorem gives us a vertical asymptote. We know it's not a removable discontinuity. Done. Okay. Okay, so maybe we'll do another example. In fact, let's write this out of the problem. Find vertical asymptotes of h of x equals to x squared plus 1 all over x squared minus 1. All right, so instead of giving you the solution right away, I'm going to pause the video and ask that you try to find the vertical asymptotes. Okay, solve this in the most detailed possible way that we can, so that in our notes, we can reference this again when looking at other problems. All right. Basically, all we need to do to apply the theorem, all we need to do is to start checking off these bits of the hypothesis of the statement, right? So that's like 3 different parts, right? That's it. There's 3 parts to it. Part 1, define f and g and your possible c's. We have a ratio, right? We have a ratio that we're trying to get to. So whatever is in the numerator is your f, whatever's in your denominator is your g, right? So part 1, define f, g, and possible c's. And there could be more than one vertical asymptote, and that's where there's more than one C possible. So looking at the thing, I say, f of x is equal to x squared plus 1. And then g of x is equal to x squared minus 1. You don't see the possible issues, the possible zeros of g, right? That's the whole thing that we're trying to get to. Where is g equal to 0, right? If you don't see it right away, you can factor this difference of squares, right? You can always factor difference of squares. You can rewrite g as x minus 1 times x plus 1. So where would g be equal to 0? At x equals to positive 1 and x equals to negative 1. So those are your possible c's that you need to check. All right, so done. Okay. Now, part 2, it's pretty easy to verify, right? F does not equal 0 at either one of those c's. I'm going to try to squeeze that in. All right, so c is equal to 1 minus 1 possibly, and in parts 2. So f of 1 does not equal 0. F of minus 1 does not equal 0. And g is equal to 0 to both of them. So second check, done. Third part is more, it's kind of like the easiest part. It's always going to be this way. Not always, but for many of the examples you look at, you just need to make sure that around those C, around them, it's not 0 all over the place. Okay, for G. So part 3. So G of 1, no, so sorry. G of X is not equal to 0 for X around C is equal to positive 1, right? So like, this is just some like parabola looking thing brought down by negative 1, right? This right here, it's not going to be 0 anywhere, like you make a little interval around positive 1, it's not 0 in there, a tiny little interval. Y'all know what that looks like, right? You'll have to know what that looks like. Parabola taken down by 1, right? So it looks like this. Oh, that's horrible, but yeah, it's like that. And those are the zeros of that function, back to 0 as a function, right? So I know that around positive 1, it's non-zero around there. And around negative 1, it's non-zero. So that's part 3 of satisfying this definition. X around there. And G of X not equal to 0 for X around C is equal to negative 1. So there's little intervals around 1 and negative 1 so that that G function is non-zero. Yeah.
I'm just trying to figure out, what does that even mean? That confuses me.
The interval?
Yeah, like.
It means that.
So if I put in like a 0.12.
This would be a bad function for G. Suppose like you had C right here. A bad function would look like, let's say, like this. That would be bad. Because then there's like, it's not going to work out right there. Actually, if you made the interval, like it doesn't matter how big of an interval that you put around C, right? Like this interval is going to be 0 everywhere in there, right? If you put that interval, it's still, all of those x's are going to be 0. So this would be a case where you couldn't satisfy part 3. Over here, like with RG, it only passes through 0 like quickly at those 1 points. It's bad when it's 0 all over the place. Okay. Okay. And we're done. This theorem implies that both of these values of C are vertical asymptotes for H. Because that's what it tells us. X equals a C right there.
So, which is 1 and -1.
Yeah, well, X equals 1 and X equals -1 because that's drawing a line like that.
Yeah. But like, put it like for like a problem one, like the homework.
Yeah.
Quiz.
Yeah.
Okay.
And that's it.
Just a weird question.
What's that?
What happens if the graph is going horizontal?
That'd be a horizontal asymptote. And we'll get to those sometime soon. Again, we can define these in terms of limits, which, by the way, we're applying the theorem here, but do we really need to?
You can just look at it.
Look at the limits, right? Look at the limit as X approaches -1. Where does this go? Do we have positive infinity, negative infinity on either side of it? Where does the function go? If this blows up, that's a vertical asymptote. This is just kind of like a procedural way of guaranteeing it with the theorem, but if you investigate it by looking at the limiting process, you should find the correct answers. Right? There's two different ways to do this. Okay. I think I'm going to go ahead and stop here. I think my leg has had enough of standing. And I will make a third video at my house on what we didn't cover, which are like the additive and multiplication properties for infinite limits, as well as like looking at examples of those things. It'll be a short, like 15-minute video, but I'll make it probably like tomorrow morning or something.
Will it be on the playlist?
It'll be on, yeah, on the same playlist.